Okay, today we'll be starting the chapter 3 with propagation in elastic media. The first two chapters, I think, introduction to earthquake and the theory of vibration, which is chapter 2. We will revise some of the concepts in chapter 3, but this is mainly, we'll be talking about how waves travel from inside the earth, especially in the case of earthquake, from the center focal point where it occurred to the ground surface where our structures are, or in the interior of the earth. So we'll look at general overview of wave propagation and these waves, nature of waves and everything. We discussed it in chapter 1, but we'll quickly review it. And section 3.2, we'll see review of stress and strain relations in soil. This is from engineering mechanics. We'll just quickly revise those stress-strain relations because they will help us to derive the equations for wave propagation in a soil media or elastic media. And we'll start with a one-dimensional wave propagation, just wave passing through like in a bar. And we'll extend it for a P wave and torsional wave. The torsional wave is also called the shear waves. They are similar in nature. They create the same shear waves, both torsion and shear. So we'll derive those equations in a bar just for one decays, and we'll extend it to 3 decays, three-dimensional wave propagation. And we'll see also some behaviors of waves, how waves reflect and refract or transmit to between boundary layers. In the 3-dimensional wave propagation, we'll have 2 cases: stress waves in infinite elastic medium. Infinite in a sense, if you are at the center of a body like some depths inside Earth, everything around you, you can assume it to be infinite. Or stress wave in elastic half space. If you are at the top surface of the Earth, then we're talking below the Earth, which is the half space. So that's section 3.4, infinite. When we say infinite, it's really, if you are deep inside the Earth, this is what we are talking. Everything is, you have a medium around you. So we call that, anything around is infinite. But when we say half space, we are really sitting on the ground surface. Somebody is standing there and we are looking at below. So we call it half because the other half is not part of the Earth we are considering. And section 3.5, waves in layered medium, reflection and refraction. The concepts that we see for general waves in section 3.3, wave reflection and transmission, we'll use them again for a layered media for a seismic case. But you can have any kind of wave. It can be a light wave, radio wave, electromagnetic wave, so many kind of wave or lights. But the way they travel, it's very similar. When they find a boundary, they either reflect or it pass through it, part of it. So those reflection, and diffraction concepts, they're applicable to a soil media for seismic waves. And we'll see inclined waves. Waves are not always vertical or horizontal. You may have inclined waves coming. But usually around the surface of the Earth, even the shear waves, they arrive vertical. Wherever it happens at some distance from the surface, when it approaches the surface, it always comes as vertical. And we'll see those concepts, why it becomes as vertical. And attenuation of stress waves. This is basically damping, because if you have an earthquake occurring at some point, depending on the magnitude or the energy content of that earthquake, it may reach certain places or it may damp out and it may not be observable at some other locations because there is some damping, and we call it also attenuation. There are attenuation relationships described, especially in seismology, where it tells you, okay, how much of the energy is propagating, how much is damping out. And that damping is usually because of the heat, particle rearrangement, friction, sound, anything, any loss of energy within the Earth. So we'll talk about those concepts, but we'll focus when we say attenuation and stress waves, we're talking mostly damping in soil. We'll not talk more about the seismological concept, which is attenuation of, in a larger propagation case. So wave, we defined it before in chapter 1. It's a propagation of disturbance from one place to the another. It is a propagation of energy or a stress wave. And you can have different forms of wave. You can have, like, if you throw a stone in the water, you may have circular waves happening. Or if you have a rope in vibration, if you oscillate up and down a rope, you will have oscillation like it. This is a wave. Your disturbance, your energy over here is propagating through the rope to the wall here or to the anchor point. This is like a shear wave. The particles are moving up and down, but the wave propagation direction is this direction. Or you may have electromagnetic waves. Electromagnetic is you have electric field, which is like the red one, and perpendicular to it, there is a magnetic field. So the electromagnetic waves are, perpendicular to each other, and this is how it propagates. And usually electromagnetic waves, they don't require medium or material to pass through. Even in a vacuum, you can have electromagnetic waves passing. And seismic waves within the soil medium, you can have, this is like a shear kind of motion. Particles are up and down, the wave is passing through here. So it's like the energy or the disturbance or the stress is passing through. But the particles are not moving together. The particles are moving up and down in the shear case, or if it is in the P wave case, it's compression and tension. They move back and forth where they are, but they don't travel long distance with the wave or with the energy or with the stress. Or you can have a sound wave. If you create a sound at some point, sound is a P wave. It creates compression and tension, and this is how it moves through the air. It needs a medium, and we can finally hear it. That's a sound wave. So when we talk about wave, it can be really any kind of wave, water wave, rope, electromagnetic, seismic, or sound, but we're focusing on the seismic waves. But the nature is the same. So the equations we derive and the reflection and refraction properties, they are similar to each other. Depending on the medium they pass, waves can generally be divided into electromagnetic wave, which doesn't require any medium to pass through, or mechanical waves, which need a medium to propagate. Mechanical waves are like sound waves or seismic wave. Electromagnetic waves, they don't need any medium. Like type of electromagnetic radiation, you can have radio waves, microwave, infrared, visible light. Visible light is electromagnetic, like the light which comes from the sun, which reaches to the earth. It passes through a vacuum, and when it arrives to the earth, there is, the atmosphere. So it can pass through either a vacuum or a material. And ultraviolet rays, X-rays, commonly used in medical examinations, and gamma rays. Gamma rays are some rays like from a nuclear radiation. That's my everyday task because I work in a nuclear power plant, and every time I get into the plant, I'm exposed to gamma rays. But we have monitoring system how much we are receiving, and we have a limit. And if we are exceeding or really at a high spot, there is alarm to tell us to get out of that area. So these are electromagnetic radiation. And mechanical waves can be classified into two categories based on the motion of the medium. It can be longitudinal wave, like a P wave we talked. If you apply a compression force on a spring, that compression force you applied, it passes as a stress wave and finally reach to the anchor point or a support point. And the way the P wave travel is there is extension and there is compression regions. So extension, compression, that's why we call a P wave a compression wave, or also called a dilatational wave because of this dilatation. Or it can be a transverse wave, like a shear wave. So the applied force, if you apply force up and down, you have like a shear. The particles are moving perpendicular to the wave propagation. Wave propagation is in this direction. Or the wave, what we mean by a wave is the stress or the energy is propagating in this direction. But the particles at any point in the spring, they are moving up and down. In the case of P wave or longitudinal wave, they are moving parallel to the main propagation direction of the wave. So if you have like a transverse wave, the high point of transverse waves are called the crests. If you have like in a spring moving up and down, these high points are called crest points. The low point is trough. And amplitude, we defined amplitude already in chapter 2. So if the oscillation is about this red line, then the maximum deflection from the 0 point is the amplitude. And the wavelengths, it's just, we define a period to be the time it takes for one complete cycle. Then that distance is what we call wavelengths. So if you know the wavelengths, if you know the period, you can actually calculate the wave velocity because it's just wavelengths divided by the period. For longitudinal waves, these corresponding pointers, in shear wave, it's easy to see them. In longitudinal wave, the cycle is defined by the compression pointers and the thin pointers. You can see it here. One cycle is from this compression zone to the other compression zone. It's the dense region to the dense region. And the wave is passing, direction of propagation is this way, and particle motion is back and forth this way. Wavelength, we defined it, is the length which takes to one period. Period is the time it takes for a wave for one complete cycle. And the frequency is really the inverse of period. It's also the number of waves or vibration past a specific point during the unit of time. And wave velocity, you can get a wave velocity if you know the wavelength is, if you know the time it takes for one complete cycle, then that's your wavelength, the wave velocity, which is equal to lambda by t, or lambda times frequency, because frequency is the inverse of time. So we have some characteristics of waves. We have a reflection character, where if a wave is bounding on a surface, it's like if you have like a horizontal surface and like a light. If a light comes here, then it reflects. And if it's a flat surface, we know that the angle of incidence is equal to the angle of reflection. And this is a law of reflection. And refraction is a bending nature of waves when entering a medium with different wave speed. Let's say you have a medium here, a slow medium, a slow wave velocity. And you have another medium here, which is a fast medium, or the velocity of the wave is faster here. So what happens is, if you have two mediums where the wave is experiencing different speeds, then the wave bends. And the way it bends, it depends on the speed, relative speed of the two mediums. For example, if the slow medium, let's call it V2. If V2 is less than V1, then a wave entering this area, let's say from the normal, it's theta 1. Then if V2 is less than V1, then the wave bends towards the normal. This is the normal. So you'll find theta 2 less than theta 1. This is, make sure you understand this concept. I know you studied it probably in physics with the refraction concepts, but it's also directly applicable to seismic waves. When we are dealing with, layered soil media later, that's how we use it. A seismic wave coming from one layer and entering another layer, depending on the wave velocities, then it may bend towards the normal, or it may bend away from the normal. For example, V1 is larger than V2. If the wave is going in the reverse direction, this way, then V1 is greater than V2, then the wave will be bending away, which means theta 1 will be larger than theta 2. So we'll see it in detail later how we apply for layered soil media. Because of this refraction concepts, you will see, a light wave has different speed in air and in water. You'll see this deflected shapes. If you put a pencil inside water, it appears like it's deflected because the light wave coming to our eye, it's deflected. Or you can see this, a person looking in a lake or in a pond, trying to see a fish, because the light reflect from the fish is going this way, this solid line, and going to the person's eye. But light has different speed in water and in air. In air, it has larger speed. If you make a line like this, which is a normal, in air, the light has larger speed than in water. So what happens is the light coming from the water, which is a reflected light, that's how we see it. We see objects through the reflected ray. Then the light reflected from this fish, then what happens is it bends away from the normal, because the V2 of light is greater than the V1. The speed of light in water is less than the speed of light in air, so it bends away. So what happens is, because of this refraction, the person thinks, we think in a straight line. We think we are looking at the fish right here. It appears the fish is in a shallower depth. In reality, the fish is at a deeper depth. This is like an illusion. This happens because of the bending nature of light, because it's entering from one medium with a lower speed to another medium with a larger speed. It also happens, when we see the horizon and the sun coming out during the morning, a person standing at one place on Earth, when it tries to see the Earth, the actual Earth is down here. It's not even out. But because the light reflecting is bending through the atmosphere and reaching our eye, but through illusion, we are looking at a straight line. We assume the Earth is right here. The Earth is already visible. So I mean the sun. The sun appears visible even before it is out because of the bending nature of light. So this is what's called a refraction. And the same way we apply it for light, it's also applicable for seismic waves. We'll see it later in detail, but make sure you understand these concepts. So for seismic case, let's say we have a rock type 1 and a rock type 2. A wave comes. If rock type 2, the velocity is higher, let's say this is V2, V1. So a seismic wave coming from a lower velocity, medium or rock, to a larger velocity, larger shear wave velocity or P wave velocity, then the wave bends away. So you see this theta 2, which is larger than theta 1. In the other case, if V2 was less than V1, you'll see that the wave bending towards the normal. So this theta will be smaller than this one. For now, just understand how it bends. But when we apply it later, I think around the end of this chapter, we'll see how it's directly applicable to the seismic wave. Then the other characteristic of waves is interference. Waves can interfere. So for example, if you have, two wave sources in a surface of water, then if you have only one source, then you'll see these circular waves. But if you have two, then you'll see interference. You'll see different shapes. Depending on the phase, depending on the amplitude, the two waves can add up. If they have the same phase, then the amplitude would be twice if they are same amplitude, or it would be additive, or it would be constructive. If they are in opposite, then they can cancel out. It's called destructive. They can completely cancel out, or it can reduce. The amplitude can reduce. So you can see zones where it is canceled out, destructive zone. You can see zones which are amplified, constructive zone. Or it can be somewhere in the middle with different phases. Some waves, some amplitude may increase or decrease depending on how they are. So that's called just interference of wave. And diffraction is another wave characteristic. It's a wave bends when they pass around small obstacles and spread out when they pass through small openings. So what it is let's say a light wave is coming from here. It's blocked by an object right here, but there is a small hole. If that's the case, what happens is when the light wave passes through here, it bends. And it bends, after this, let's say it's a free zone. So it tries to spread. It gets bigger. So that's the diffraction nature. Now this has a direct application to seismic. Because of this, we have a damping called geometrical spreading. So geometrical spreading is because it bends. So it's now, if it was straight moving here, if it doesn't bend, then all you have is this. Same wave passing through. No length change, no spreading. But because it bends, now because of this bending, it's radiating, in every direction after that. Or it tries to expand. So that is called geometrical spreading. Radiation damping for seismic waves. We have two dampings for seismic case. One is material damping, or we call it viscous damping. The other one is radiation damping. Radiation damping is because when a wave enters a larger area, it spreads out. It was small right here. Now it's bigger here. It's covering larger area. But the concept is the energy of this wave is the same as this all energy, but it's spread in a larger area. And because it's in a larger area, the intensity gets weaker. So just because of a geometrical spreading, the wave gets weaker and weaker. When it has high intensity when it's at the beginning, but the intensity decreases as it spreads out into a larger area. That's called geometrical spreading, or we call it radiation damping. Radiation damping is a concept where intensity of the waves decrease by geometrical spreading when entering a larger area. So this is different from a material damping. Material damping occurs when, through friction, when one particle slides over the other, or plastic deformation like that, we have a material damping. Energy gets absorbed through friction. But in our radiation damping, the other damping is radiation damping. It's purely because of a geometrical spreading. Because it's spreading over a larger area, the wave is getting weaker. That's the concept. Seismic waves, we discussed this. I put it here just for a quick review. Seismic wave, we can have a body waves, traveling through the interior of the Earth, or a surface waves. Once it reaches to the surface, then it travels to the surface wave, lava wave and relay waves. Seismic wave, you can have a body wave or surface waves. Body waves, we talked about P wave, which is a primary wave, the wave which arrives to the recording station first, or lava waves. Secondary waves, which is S waves. The surface of they can be lava wave and relay wave, depending on the particle motion. And secondary waves, shear wave, they can be SH or SV, depending on the plane the wave is passing. So seismic wave, we discussed already this on chapter 1 in detail, so I will skip it. So P waves, like we discussed, it's very similar to a longitudinal wave if you apply a compression force on a spring. The wave propagation is through the expansion and compression of the material. And the particle motion is in the same direction to the wave propagation direction. S wave, in the case of S wave, you have like this oscillating kind of vibration. A particle motion is like up and down, which is perpendicular to the main wave propagation. Or it's very analogous to a wave. If you apply, a transverse wave on a spring, that's just a good example for shear waves. Shear waves, we say they can be SH wave or SV wave, depending on the plane of propagation. If it's propagating in a vertical plane, we call it SV, which means S on a vertical plane. If it's propagating on a horizontal plane, we call it SH. Otherwise, it's a particle motion. The wave propagation direction is in this direction for both. But one is the particles are moving in a horizontal plane, so SH. In the other case, the particles are moving in a vertical plane. We call it SV. Rayleigh waves, we discussed this. They are surface waves, and the particle motion feels like in a circular. So somebody standing on the ground, he feels like the ground moving up and down, but the particle like thrown out like this. So good example is like if you have, telecommunication towers or power cables, you can feel the ground cracking at the crest points. These are the crest points that we talked, or these are the trough points. Love wave is a surface wave again, except that it's a shear wave. Both are shear waves, except that the direction of propagation of a wave is, let's say it's in this in this direction, and a particle motion is sideways. In the case of Rayleigh wave, it feels like moving in a circle. But in the case of love wave, it's like a sideways. If somebody stand here, they will be like shaken sideways when the wave passes under these. And seismic wave reveal the inside of the Earth. Now the seismic wave have big application, especially in the past, in the 1930s and afterwards. Seismologists and geophysicists, they discovered the solid inner core. I think a scientist called Lehman, it's a Danish scientist, Danish seismologist, discovered a solid core in 1936. This discovery is by observing how the seismic waves travel through the interior of the Earth. Let's assume we have an earthquake around the surface of the Earth, the shallow depths. And then we have waves traveling throughout any direction. It's a 3D. You can have P wave and S wave recorded, let's say, in this region. We know where it occurred. So you can also record the P wave and the S wave in this direction. But now, the liquid outer core, the core, it has a solid core. It was unknown before 1936. It was assumed to be liquid, because in the liquid zone, what they observed is, we know that shear waves don't propagate through liquids, right? So because this is a liquid, once this P wave touch this area, you will not see any shear wave propagating in this zone or recorded in this zone. Why? Because shear wave don't propagate through liquids. This is liquid. That's how they discovered it. They discovered only P waves in this area. Let's say an earthquake occurred in Japan, and when they recorded somewhere in New York or Europe, they record only S waves. They record only P waves. They don't see the S waves, because then they realize, oh, it must be liquid in this area. So the liquid outer core is discovered. Then, even in the core, they discovered there must be solid, because the P waves passing, coming from the epicenter, going through the liquid, they are not observed at the same location where they were expecting it. There is some bending. This bending is the refraction we talked. Because they have different velocities, the P waves in a solid and the P wave in a liquid, it's different. So there's some bending happens. And this bending is not consistent. You see, there is some bending at the liquid interface, there is another bending at the interior area. So by observing this wave propagation and the bending characteristic, this Danish seismologist concluded there must be a solid inside the interior of the core. So that's when the inside of the Earth is determined to be a solid. So at the center, you have a solid, and outside the solid, the outer core, it's liquid. Then the crust mantle, you have it at the top. So that's how the discovery of the interior of the Earth is really by observing seismic waves from different recording stations and analyzing those waves. Nobody really went down to the center of the Earth to see whether it is liquid or solid. All this, the interior of the Earth's discovery is through analyzing the seismic waves from recording stations. So now that's the discovery of the solid inner core and the liquid outer core. So once you are, in the liquid outer core, you have only P waves. So look at these regions. This area, we said no direct S wave. There is no S wave from this to this area. Why? Because the waves touch the liquid zone and they are no more appearing. Shear wave doesn't propagate in liquids. But you will see shear waves in this area. And now, even for a P wave, look at this area. The earthquake occurred here. We have a P wave coming, and the P wave enters the liquid outer core. It bends from the solid inner core and comes around here. So we have a region, this gray area, where we're not recording any wave. We call it a P wave shadow zone. Because of the bending nature of the waves, we have a region where we're not getting any P wave. P wave can pass through liquids, but because they bend away, this area is not any recording station in the world. If it's in this zone, it's not going to feel any earthquake. So if an earthquake somewhere in the world, it doesn't mean that all recording stations will record it. Most of them, they'll record it in this area or in this area, in this zone. But if you are in the shadow zone for P wave, you will not record any S wave or P wave at all. That's a big concept. So these two symmetrical areas, P wave shadow zone is the area where no seismic record will occur because the waves are bending away. But if you come this area, the yellow area, you can record waves. So for S waves, the entire lower area is a S wave shadow zone because you're not recording any S wave. So you can really tell, depending on where an earthquake occurred, you can tell which recording stations are going to record it. Some of them, they are going to miss it because they may be here. Or, I mean, we're talking about a larger earthquake, a larger magnitude earthquake. If it's a small magnitude earthquake, it may not be felt by faraway recording stations. Let's assume a big earthquake occurring, then that big earthquake, it can be felt anywhere in the entire world, except these shadow zones. So you can read more about this discovery of the interior of the Earth and these shadow zones. I put a link here. If you are interested how they discover the interior of the Earth, you can look at it. Section 3.2, review of stress and strain relations in soil. Now we're getting into more the calculations, the derivations of the equations. Now we know by concept, we know how waves travel, how they reflect, how they refract or diffract. But before we get into the more mathematical formulations or getting equation for the wave, we'll review some stress-strain relations. This is basically from your engineering mechanics. So section 3.2 is just a review of the engineering mechanical relations. because the propagation of waves through a solid media, it has a bigger application for geotechnical engineering. We can determine the elasticity, the modulus elasticity, shear wave velocity, shear modulus, and also, we apply waves for determining the stratification of soil. So it has a big application. Through waves, you realize from the previous slide, we understand the interior of the earth because of earthquake. If earthquake doesn't occur, we have no idea how to deter what's inside of the earth. But because earthquake occur, waves pass through, and analyzing the waves bending, reflecting, and the shadow zones, we can tell, okay, this is the interior of the earth. This is a liquid outer core. It's this distance from the surface and things like that. And the same is true for shallow layers. If we are around the building, we can really tell the stratification of the soil. We can say we have, okay, clay soil, sand soil, gravel, all the stratification we can determine it, depending by analyzing waves passing through the soil. So before we do that, we will start with waves passing through in a 1D, like in a bar. We'll just create a bar, we apply a force on it, and see how that stress wave propagate through it, and try to find the equations of the wave. And we'll solve it, and we'll try to determine the shear wave velocity, the P wave velocities of that wave. And that 1D bar will stay extended into infinite elastic media. When we call it infinite, we are deep inside the earth. We have, like, we can take a cube element deep inside the earth, so it's under compression or stresses from all directions. Or we'll extend that concept also for half space. Half space is there is no stress at the top, but if you take element which is free stress at the top, then but it's stressed from other three directions. So knowledge of the fundamental definition of stress, strain, and other related parameters that are generally encountered in elastic medium is essential before the relation for a stress wave can be developed. So our idea is we'll review these stresses from our engineering mechanics, then we'll apply it to derive the equation of a stress wave in a soil medium. So normal and shear stress notations, let's say you have a cube. Assume this cube is taken from inside of the earth. So it has stresses, normal stress at the top and two shear stresses. Same at the bottom, except magnitude may change depending on this weight. And on the lateral face also you have a normal stress sigma x and shear stresses. And the shear stress notation, you can assume when you say ij, I is the direction of, for example, sigma x is the normal in the x direction, and shear stress xz, x is the direction that's perpendicular to. For example, this on this face of this cube, x is perpendicular. So when you talk about this shear stress in the xz direction, which means the x is the direction it's perpendicular to, and the z is the direction it's going, because it's in the z direction. That's the notation. So for this thing, so you have all 6 faces. There are 6 faces or 8 faces. 1, 2, 3, 4, 5, 6 faces. So in all 6 faces, you have these stresses. So if this cube is in equilibrium, then some of these forces must be the same. For example, this sigma x, you see it horizontally, it should be sigma x, except the direction. So for horizontal equilibrium, the same is true. Sigma y in the y direction should be the other sigma, except it's in the opposite. The same is true for sigma z, the vertical direction at the top should be the same as sigma z, except it's in opposite direction. So for this element to be in equilibrium. The same is true for the shear stresses. This shear stress on this face should be the same as this shear stress on the other face. XY should be the same as XY, except it's in opposite direction. Or this shear stress in the ZX, shear stress in the ZX direction. except they are in opposite direction. So due to given stress condition, let the displacement in the x, y, and z direction be respectively u, v, and w. So we'll consider this displacement. Let's say that solid element has a deformation u in the x direction, v is in the y direction, and w is in the z direction. The equations for strains and rotations of the elastic and isotropic material in terms of displacement are as follows. Normal strains, that deformation in that direction over the length of that element. Or it's a partial derivative we are using because we are making derivation with number of elements. So for that small infinitesimal element, we considered the delta U by delta X, the strain in the X direction. For the Y direction, the deformation in the Y by the length of that Y direction, and strain in the Z direction, deformation in the Z by the length in the Z direction. And this is normal strain. The shear strain is a deformation in the two axes. It's given by this. The deformation in the Y along X, the deformation in the X along Y. So you have this shear strain in the XY, YZ, or ZX direction. Or rotation of that element. It can be rotation, we're talking the same element here. It can be rotation about the Z-axis, or Y-axis, or X-axis. Those stress relations can be developed by this, depending on which axis you are considering, for the X, for the Y, and for the Z. For elastic isotropic material, when we say isotropic, we mean it has the same property in every direction, the same density, same void ratio, or anything, your E, like elastic modulus, or G, shear modulus, they are all the same. That's what we mean by isotropic material. The normal strains and normal stresses can be related by the following equations. For 1D case, now we are relating strain and stress. For 1D case, strain is stress divided by the elastic modulus. This is the normal strains we are talking. If it's a 3D case, 3D cases are element. You have stresses in the either direction, so we have to consider them, sigma y and sigma z, and we have also the Poisson ratio. If it's 1D, like strain in the x direction, then this is 0. Then we're talking about stress in that direction by elastic modulus. But if you have a 3D case where the stress are, you have sigma y and sigma z, then this is the relation. So this is just a review of your engineering mechanics because we're going to use it to derive the wave equations. The same is true in the strain in the Y and strain in the Z direction. Shear stress and shear strain can be related by the following equations, same as like the elastic modulus. For shear case, we have the shear modulus. When we talk about shear wave velocity, S wave velocity, we are mainly considering the shear modulus. When we talk about elastic modulus, that's more for P wave. It's like a compression and dilatation. But shear is like particles are moving in the perpendicular direction. So the shear stress and shear strain can be related by this. And the shear modulus is also related to the elastic modulus. It should be familiar to you. Shear modulus is elastic modulus by 2 times 1 plus the Poisson ratio. Now, if you rearrange the previous equations, then we can have a normal stress in terms of normal strains. If you do some math, some algebra on this, you can have the normal strains expressed by normal strains. This is for 3D case, where E bar, epsilon bar, this is a Greek letter, I shouldn't call it E, this is epsilon bar, E is the volumetric strain. strain in the X, strain in the Y, and strain in the Z. G is the shear modulus. Should be same as this. Okay, this is a volumetric strain. It's the sum of these three, but this is a strain in the X direction only. And lambda is known as the Lames constant. It's just this, it's in terms of Poisson ratio and elastic modulus. Can easily be estimated by a relatively easy measurement of the elastic modulus and Poisson ratio. Mu can be expressed in terms of lambda and G with this relation. So this is just a quick review. You can go, if you need to understand it better, just go to any engineering mechanics book, strengths of materials book, you'll find all these relations. Or our reference, I think reference to has more detail. That's where I took it from. You'll find more detail about it in reference to. Now, let's get into a one-dimensional wave propagation. We reviewed our stress-stress relationship. We looked at wave characteristics. And now let's try to have a mathematical formulation for a wave propagation. Our goal is finally to find, how the shear wave, what's the velocity of the shear wave, what's the velocity of the P wave. That's our target. So let's start by a simple example where we have a bar, apply some load at the left end. Just hammer it. The hammering force or the stress you applied here, it propagates. We're applying like a P wave because the particles are moving, in dilatation and in compression and finally reaching to the other end. You have a compression zone, you have a refraction zone. It's similar to applying that, a spring load at one end, like compressing a spring at one end. Same as the example we saw before. Take a small section of this bar, anywhere, and let's analyze this element. Take a section AA and BB, and assume it's delta X element, a small infinitesimal element that we are considering. Assume that is X distance, and that's why we call this delta X is the element we want to analyze. And the deformation in this area is U. X is this direction to any deformation is U. Now, let's see, at that element, for equilibrium to occur, we're considering only one direction. Forget about the vertical and other orthogonal direction, which is Y and Z. Consider only X direction for now. We're trying to simplify and get how this wave travel and trying to get the wave equation and the wave property. So that wave I applied, or you applied at this point, let's say it's a stress. At section AA, let's say we have this stress. But when it traveled through this element we considered, through delta X, it changes. So we'll have sigma plus some rate of change of that stress with respect to X. Why it changes? Well, you can have damping. You can have so many things. So we're not expecting identical stresses at this point and at this point. Or the stress you applied here is not going to be identical to the stress you will record here. You will see some loss. It can be through damping or it can be through anything. So there is some change. For now, just assume there is some change. Now, the stress increase along the section BB can then be given by, it can be increase or it can be decrease. Most probably it's a decrease because of the damping nature. But assume that's going to be like this, that change. If you use Newton's second law, for this element to be in equilibrium, these forces has to be equal. Now, since this is a dynamic motion, it's not static. we have Newton second law tells us summation of the forces should be the mass times acceleration. Summation of the forces is what? You have a force here, and you have the force here, which is, let's say, that force is this stress times this area is in the negative direction, right? So stress times A is the force on the left side. And the force on the right side, it does this stress and that change times the area. We're assuming the same element with the same area on both sides, equals to mass times acceleration. Is that deformation? This is your acceleration, rate of change of that displacement. And the mass is, you can determine the mass of that element. The area times the unit weight times delta x by g will give you the mass. Now, if you solve this equation, you will arrive to this equation. U is displacement of the bar in x direction. So this is the same equation we get from the previous slide. However, note that stress is what? Strain times Young's modulus, right? That's from the previous section. If you know, we define the strain is stress divided by Young's modulus. Why we call it Young's modulus E? Because we are dealing with a compressional stress. If it was a shear stress, we call it G. The strain is defined like this in our stress-strain relation. The deformation about U axis and that element in the x-axis times E. Now put that back in the equation. So replace stress. If you put that here, this is what you get. Your original equation and replaced with this. And simplify it further. And finally, you'll arrive to this equation. Second order partial differential equation. Now, this is the one-dimensional wave equation. Partial differential with respect to time and displacement. Now look at VP right here. That's where we are most interested. VP is the square root of E by rho, because we have E by, this is density of the material or the bar. E is the elastic modulus. Both are known. Now this is giving us the primary wave velocity of that bar. This is a wave equation. In the wave equation, the VP is giving us the primary wave velocity or the compression wave velocity. Compression or longitudinal, this is a primary wave, or you call it P wave. This is the outcome we are most interested. The general equations of motions of the wave, I want you to understand it. I want you to see how it is obtained. But as a geotechnical engineer, we are more interested in the wave property, because we'll have a soil with elastic modulus and density. And I'm going to ask you, what's the primary wave velocity in that soil? No matter how strong an earthquake is, the primary wave velocity in a medium, it's constant. E is constant, density is constant. So if you have a strong earthquake or a weak earthquake, the wave travels with the same speed. That's a key point. The difference between a stronger and a weak earthquake is how far they can go, because the weaker one will dump out and it doesn't travel much. But in terms of the speed they are traveling, they travel at the same speed. This is the VP. Now you can assume this further into E. You can use constraint modulus. If you have a bar which is constrained means it's not moving, it's not free from the other direction, but it has a constraint, but the wave is still assuming you travel this way. You can use a constraint modulus. It's the same equation, except M now, the constraint modulus is given by the elastic modulus, and the Poisson ratio function. This. So you can have a free bar or you can have a constrained bar. If it's a constrained bar, you'll use M, which is constrained modulus. This has application. We'll see it later in soil, because if you are considering a wave propagation deep inside the earth, and if you take an element deep inside the earth, it's constrained. It has stresses all around it. So in that case, this is more applicable. But if you are, considering a wave traveling around the surface, like a surface wave, Rayleigh wave or lava wave, it's free at the top, right? That's more applicable to the E, the elastic modulus. So depending on the element, in this case, we're considering a bar. So the bar was free, so we use elastic modulus. But if you assume it's constrained from all direction, you can use constrained modulus rather than elastic modulus. Yeah, the other consideration is this conclusion. Note that the velocity of wave in a constrained bar is faster than the one in free unconstrained bar. This is because the constrained modulus is larger than the elastic modulus. It's clear. If you do the math, this equation is greater than the E itself. And there is another concept which is very important for us, which is called particle velocity. There is a wave velocity and particle velocity. When we say wave velocity, we're talking the energy, the stress that's propagating. Let's say you have a shear wave or a P wave passing. When we say particle velocity, we are talking about the particles. Okay, the particle around here, in the case of shear waves, they are moving just up and down. They are not moving together with the wave, with the energy or stress. That's the particle velocity we are interested in. Or in case of compression and tension, the particles are moving back and forth this way, in the same direction to the main wave propagation. But the particles are not moving with the stress. They are not moving with the energy of the earthquake. Rather, they go back and forth where they are. That's the particle velocity we are interested in. So if you use the stress-strain relations from our mechanics, U by X, a normal strain displacement relation, the deformation in the X direction, and the length of the X direction, that's called strain in the X direction. Or stress-strain relation, you have the stress by the elastic modulus is the strain in that direction. So we have this strain relation, stress-strain relation, and a wave velocity. Because we are talking about E here, it's a P wave. For a P wave, we know that the wave velocity is given by the distance it traveled with time. That's the wave velocity. Or the wave velocity in a constrained bar, we say it is square root of elastic modulus by the density of the bar. That's what we just derived right here. If you put together all these three, you'll find the particle velocity is that U is the deformation around the particle. The particle velocity, the displacement of the particle with time. And now, though you can replace it with this. And strain in the X direction, you have it in the form of sigma X and elastic modulus. You can replace further. And also, what did you replace? Dou X, this one. The deformation X is the VP times change in T. If you do all that and simplify it further, finally you'll find the particle velocity is given by the stress you applied divided by the density of the material divided by the VP, the primary wave velocity in that direction. The same is true whether we are doing a P wave or a shear wave. So the particle velocity is given by the stress applied divided by the density and divided by the P wave velocity. Or you can rearrange this. You can find the stress is equal to the density of the material, the primary wave velocity, and particle wave velocity. For now, just understand that a particle velocity is determined this way, but we're going to use this concept later. When we talk about damping infinite bar, we'll use this equation. Just for now, keep in mind that a particle velocity can be expressed in these forms. That discussion was for a P wave in a bar. How about a torsion or a shear wave? When we say torsion, it creates the same stress like a shear stress. So whether we call it torsion or a shear stress, it's the same thing. Now let's assume instead of a force you applied like hammering one side of the bar, let's assume that you are twisting it by applying moments. So you're creating a torsional wave. It's not a static force we're talking. It's like a dynamic, constantly applying it. If we twist it, then what's going to happen? Consider the same, this small element in a bar. And if you see the free body diagram of that, you have in the momentous, the torque you applied, that torque, let's assume it's fixed at one end. You can assume you applied your torque at the other end. And we're going to see how that torque changes. That torque you applied on the left end, it changes when it passes through that because it twists, it deforms that element. It does some work. So it changes. It usually decreases because it created deformation or twisting. So the rate of torque within that element by the length of that element is what changes. We can apply now the same concept, Newton's second law. The summation of these forces, now we're talking more of torsion. The summation of these moments should be equal to the angular momentum, the angular acceleration, the mass times the angular acceleration. So apply Newton's second law of motion for dynamic equilibrium. So the torque on the left you applied minus T plus that change in torque equals to the mass times acceleration, but now it's a rotational acceleration. And the mass is polar moment of inertia, because it's a rotational mass we're talking. The torque rotation relation gives us, this is from engineering mechanics. If you apply torque at one point, if you want to find at any other point, the change of twist, or because you're rotating it, you're twisting it, times J, polar moment of inertia, times the shear modulus. Take this key point. Because we are talking torsion now, torsion is similar to shear. We're considering G. We're not considering E, which is the elastic modulus. And if you further substitute all this and simplify the equation, you'll arrive to the same similar equation for a wave traveling in a torsional way, in a torsional bar. Or if you twist it, that's how the wave travels. It's very identical, except now we have rotation. For a bar that we applied a compression force, it was U, it was displacement in the X direction. But now we're twisting it. So it's a rotation, theta, instead of U. Otherwise, the equation is the same. The wave equation is the same. Now, take this key point. We got Vs squared. Vs is square root of G by the density. It's the same, identical to the P wave, except now we have shear modulus instead of elastic modulus. Because a P wave, like compression and tension, it requires E. But a shear wave, we need to have the shear wave, the shear modulus. So Vs is the velocity of torsional wave. The torsional wave, it creates the same shear stress. It's also called shear wave. There is a lab test where you apply a torsion on a soil sample and trying to find this Vs and trying to find the G. You record it, you apply torsion force at one end, you record at the other end, then you try to determine the G. But we'll discuss that in chapter 5. But for now, the takeaway is just make sure you understand how it is obtained, but our focus is on the final product. In a bar, we can determine the shear wave velocity or the torsional wave velocity by using a simple equation, the square root of the shear modulus divided by the density. That's what we use for our application. The derivation part is just to make sure that you understand how it's obtained. You may not give it, if you are doing future research, you may go deeper into it. But for this course, our focus is on the final products. How we determine the shear wave velocity in a soil. If I give you the shear modulus and the density of the soil, you should be able to calculate the shear wave velocity. If I give you elastic modulus and density, you should be able to get the primary wave velocity. That's the takeaway. Solution of one-dimensional wave equation. This part is taken from reference 1, section 5213. If you need, I try to put as much as I can. All the slides are self-explanatory, but if you need more detail, you can go to those sections I'm referring. I think reference 1 and reference 2 are the main references I took this chapter 3. But if you are specific to this section, you can consider this section 5213 in reference 1. So one-dimensional wave equation, the wave equation in a bar. We know that this partial differential equation for the wave. This, we call it U when we consider a primary wave or a P wave. And we call it theta when it is a torsional wave. And the V here, it can be VP or VS. Depending on if you are considering a primary wave, it's VP. If it's a torsional wave or shear wave, it's VS. For this second order derivative equation, partial differential equation, there is a solution from your advanced math. That solution has the form of this. Or it's simplified into the same as this, the ones you see the equations at the bottom. It has two components. The solution of this partial differential equation is very interesting. It has a wave, it's giving us two waves. This is one wave, this is another wave. This wave, by a function of f, vt minus x, displacement of wave traveling in the x direction. Let's say you have a wave x. In the x direction, the wave is traveling in this direction. We call it incident wave. The incident is the one you initially applied, and it's going in this direction. It's like a light ray. It's the first one to come, the original one. Argument Vt minus remain constant as x increases with time. As you go further, the time increases, x increases, this argument remain the same. And the g function, displacement wave traveling in the negative x direction. That's the interesting part. This is telling us there is also another wave coming backward. Actually, at the same instant, if you consider it at time t after the wave is generated, there is a wave going forward and there is a wave coming backward. We call it reflected wave. What it's telling us is after some time, the wave, which is the incident wave, it's reflecting and coming at any time. And at any time t, you'll find two waves, one going forward, the other coming backward. You have incident wave and the reflected wave expressed in the same wave equation. And if you go to the next section, that will be more clear. So this is the solution of that wave equation. You have two components. Don't worry about the constants right now. D, C, this is complex terms. Just understand what this means. At any time t, it's telling us there are two waves. At any point you go, there are two waves. A wave, for example, if you have a wave going back downward, there is already reflection coming, and there is another wave also going the opposite direction. Or if you see it in a bar, what it means is a wave is generated originally, there is incident wave, and reflected back at a boundary, and that's what a reflected wave. And at any time, at any distance in the wave, you can find these two waves. And some of the wave is also, it passes through. Remember the concepts of reflection, refraction, and also it reflects, the incident wave reflects, and it refracts some of it, which means transmitted. That's what the equation, the wave equation, telling us. So it's trying to tell us there can be two waves at the same time. The wave that is incident and the wave that's reflecting at boundaries. Especially in soil, even if we assume it's isotropic, it's not. In reality, it's different from point to point. So you have waves going back and forth. And a wave number, it's another concept. If you look at the charts, wavelengths, we defined it, if you have a displacement versus time plot for the wave, then from crest to crest, or the time it takes for one complete cycle, we called it period. If you know this period, and if you have a displacement, this particle displacement versus distance plot, you can have like a wave, like a Rayleigh wave from crest to crest. We call that wavelengths. So wavelength is basically the wave velocity by period, but wave number is the same as the angular velocity. For a time plot, we have angular velocity for a period. For a distance plot, we have k, which is a wave number for wavelengths. That's what it is. And k, you can determine it to be 2 pi by lambda. So the plots, the difference in the plots is as a function of time and as a function of distance. For Rayleigh waves, actually on the ground surface, you can see these crest points. And the distance between the crest points is your wavelengths. Wave reflection and transmission at boundaries. Now we're getting into a more practical application of this wave. Because in geotechnical engineering, that's what we want to do. We want to create a source like hammering. We're not dealing only with seismic waves. Sometimes we create artificial waves. We hammer the ground to generate waves. Those waves go down, reflect at a boundary, come back, and we put geophones on the ground surface. We record them. And we know the distances where we put our geophones from the source. That's known. Depending on the time, the arrival time, there are waves reflecting here, arriving here, another wave coming here, another wave, they may refract and pass through here and recorded at larger distances. Based on this, and there are some waves entering the other layers. And by recording the different arrival of these waves through our artificial source, we can determine the thickness of layers. The overburdened soil, we can tell, oh, this is H depths. In this case, we have two layers, bedrock and overburdened soil. But if you have multiple layers, we can do that. We'll see it in chapter 5, I believe. We can see, artificially generated wave. It pass through, depending on the density, it may bend away, and it may bend away like this. So we can tell this is H1, this is H2, this is H3. So without making boreholes, without taking soil samples, we can actually determine the layers stratification of a soil using artificially generated waves. Remember, seismic waves, they help us to determine the interior of the Earth. We can say crust, mantle, core. Even in the core, we say the solid core and a liquid core. We did all that without going deeper into the core. That's all by analyzing the property of the waves. Similarly, if you apply a source at like hammering, like a small wave at the source, at the ground surface, and record it through geophones, we can analyze those waves and determine our soil stratification. That's one method now commonly used, in addition to the borehole technique. In borehole technique, you have to drill holes deeper, 100 meter to 100 meter, and several of them, then you can determine the stratification. But this is becoming very popular now. It's cost effective. It can easily be done. Within a few hours, you can finish the entire site. This concept is also, this is basically because of, remember what we studied in a bar. We applied a load, we created incident wave. There can be reflected wave at any time, or some waves can be transmitted. So we can have equations. The incident wave, the reflected wave, and the transmitted wave. These in complex forms. But our takeaway for our geotechnical engineering is, because of this nature of waves, seismic wave or surface waves that we generate, and by analyzing those, we can get soil stratification. That's the takeaway here. And we know that if I have a soil here, if I know the shear modulus from lab, and if I know the density of the soil, I know the shear wave velocity or the P wave velocity. That may be a good point to take a break, and we'll discuss it after the break, the section 3.4.